I am the JavaScript engine. This is the most yellow thing I had to wear. And I am your JavaScript code. He does whatever I ask him to do. Watch, watch. Hey, what time is it? 9:01 a.m. What day is it? Saturday. What is your name? Oli. Of course. These are questions he can answer right away, also known as synchronous operations. Now, watch this. Hey, can you give me some water? Sure. See, now that's an example of an asynchronous operation where he actually has to take some time and go do the thing that I need him to do. So I can wait, and I do wait like this. And he's back, thank you very much, cheers. And what if I don't wait? What if I ask a second question before he comes back, right? Let's see what happens. Hey, can you give me some coffee? Sure. Hey, can you sing me a song, but not a lame one, a good one? He can't do it because he's already gone fetching some coffee for me, right? So that's an example of an asynchronous request. So what do we do then? We have to wait either for him to come back in real life and then ask the second question, or I have to leave him a note, or maybe he has an assistant that can organize his tasks for him. Either way, that's a problem. And the solution in JavaScript is called the event loop. Hello, beautiful babies. In this episode, we're gonna cover what the event loop is, the call stack, the task queue, the microtask queue, all the technical stuff. I'll show you plenty of code examples and lots of animations. I know we all love those. And the most important of all, why should you care about any of this? This is episode 18 of this 20-part series I'm calling 20 Things JavaScript Developers Should Know, but Probably Don't. This is episode 18, the beloved event loop. Let's do this. Where's my goddamn coffee? Oh, it's right here. Never mind. Poor guy, he brought it. It's right here. Now, it all starts with the fact that JavaScript is single-threaded. That means it can only process one thing at a time. But very, very often, we need it to do multiple things at once. Remember this? Hey, can you give me some coffee? Hey, can you sing me a song? You can't do it. Let's try to write the code for that. To the browser. All right, so let's do get coffee. Okay, and that is a function. And it does console log getting coffee. And then we have, what do we do? First, we're gonna do the synchronous version of this. Do sync stuff. Do sync stuff. And then console.log coffee is here. Here. Function. What's the second thing we wanted to do? Get coffee and then sing a song, right? Sing a song. What does sing a song do? Sing a song. Let's say it's just a console log, right? We're not doing anything fancy here. I'm doing start singing. Start singing. Okay. And then from here, we need a function for do sync stuff, which I am going to write here. I'm just going to copy pasta from my other window. You don't have to worry about this, but when we run this code, oops, apologies. I have a thing here. Let's go. So when we run this, it says get coffee. Coffee is here. Then it starts singing. It basically freezes the app until the coffee is here, right? So let's try this one more time. I'm gonna rerun this. While I do this, I can't interact with the app. I'm clicking everywhere and it doesn't do anything, right? So it basically freezes the app for me. This is because it's synchronous code. Let's convert this into asynchronous, shall we? So I'm gonna have the exact same code up here, except it's now doing do async stuff, and it's passing it a callback. I'm gonna have my function do async stuff. It takes 2.5 seconds. Let's do that. And here you get something totally different. Getting coffee async starts right away, and then we start singing right away. We don't have to wait for the coffee is here to start singing. And the app also isn't frozen. I'm gonna run this one more time. Let's see. Bam, and you can see I can interact with it while the coffee is being made. So now how is this possible? If JavaScript is single-threaded, how can I do multiple things at the same time? Well, that's because the JavaScript engine has a mechanism to handle incoming tasks, almost like an assistant, and the event loop is a key part of that machinery. But it's not the only part. It's actually one of 3 or 4 pieces. So in order to understand the event loop, we have to understand those other 3 things. And the 3 things are the event loop, the call stack, and the task queue. Trust me, it will make sense. And no, this is not just technical jargon. It's actually really important and useful stuff. So bear with me, we're gonna get there together, trust me. The call stack keeps track of what's being executed and their order. The call stack is a stack, like a stack of books, like that. When a function is invoked or called, it gets added to the top of the stack. Then it starts executing, and once the function is done executing, it gets removed from the stack. For example, say I have a function here called sayHello. When I call it, it gets added to the stack, the engine will run through it, and once every line of that function has been executed, then it will get removed from the stack. Another option, what if I have 2 functions, sayHello and sayGoodbye, and I call them one after the other? SayHello gets added to the stack, but not sayGoodbye, not until sayHello is done. At this point, the program is basically paused. Thankfully, sayHello doesn't have a whole lot in it, so it gets done real quick and gets removed from the stack. Then the engine goes and moves on to the next line, which is the invocation of sayGoodbye, adds that to the stack, and eventually it gets removed as well. The point is one function execution needs to end before we move on to the next line and add the next function call to the stack. Well, in that case, why do we need a stack? Well, if during the execution of one function, in this case sayHello, say before sayHello is done, it calls another function, aka a nested function call, and it could be anything, it could be just a console log, then that function invocation gets added to the top of the stack. And that's why it's called a stack, because functions can get piled on top of each other. But remember, only if they're called from inside one another. And also remember, stacks as a data structure follows the last in, first out principle. LIFO. So console.log gets added to the stack, and once that's done, it prints the message in the console, and then it gets removed. We continue, get to the bottom of sayHello, and now that's done, and then it gets removed from the stack as well. Espresso time. Let's have another example of nested calls. Let's say I have 3 functions, fun1, fun2, and fun3. Fun1 calls fun2, fun2 calls fun3, and fun3 is useless. It doesn't do anything. So the sequence would look something like this. The call stack is empty. Fun1 is called, and that gets added to the call stack. Inside fun1, we call fun2, so that can get added to the stack, so it goes on top. Fun2 then calls fun3, so that gets added to the call stack. Fun3 does nothing, so immediately we get to the bottom of fun3. It gets executed completely. We'll remove it from the call stack. We'll go back to fun2. Fun2 is also done. It completes its execution. We remove it from the call stack, and then fun1 is also complete at this point, and we remove it from the call stack. And we're done. I can't have a sip of espresso for every example, can I? Okay, so now that you know how to visualize and think about function executions, let's run through the sequence of our synchronous example from before. So to remind you, here's the code. So let's go through it. Call stack is empty. Get coffee is called and gets added to the call stack. Should we add sing a song to the call stack? Nope, not yet, not until the previous function is done. Also because it's not called from within a currently executed function, which is get coffee. So inside get coffee, we have a log which says getting coffee. Great, that gets executed. Getting coffee is printed to the console. Then it's removed from the call stack. Now we get to do sync stuff. Right? That's called, so that gets added to the top of the call stack. Do sync stuff performs a bunch of heavy stuff, right? I hid it from you, but all you need to know is that it does a bunch of heavy computation. So at this point, nothing else can be executed until it's done. This is why sing a song is blocked. It can't execute. So we don't see the result of sing a song yet. We haven't called it yet. So once do sync stuff finishes, that gets removed from the call stack. Now we can resume. So now we move on to the next line and get coffee, which is another log. Coffee is here. I mean, it took a while for the coffee to get here, is all I'm saying. That's okay. So that gets printed to the console, and now get coffee is completed. We remove it from the call stack. With the call stack now empty, now we can proceed to the next function invocation, which is sing a song. That gets called, added to the call stack. Inside sing a song, we have another log, which is pretty simple. That gets executed, prints the thing to the console, and we are done. So hopefully that helps visualize why this is terrible synchronous code and why it freezes the app. Well, if you thought I was done giving you examples, I am not. Although I am done with my coffee, so I'm gonna have a sip of water to stay hydrated. It's fucking 95 degrees out there. So now let's take a look at the async example of the same thing and why that does not freeze the app. We're getting to the good stuff. We're about to learn a few new concepts here. To remind you, this is the code. It's very, very similar. Call stack is empty, get coffee is called. You know this part. We go through the first log, then we get to do async. Do async stuff is called with a callback this time. This is new. So we add that to the call stack. Inside do async stuff, there's a set timeout. I showed you this one. I didn't want to hide this one from you. Set timeout is called with a callback itself and a 2-second delay. So the thing about set timeout is that it's a part of a web API. So we hand off the logic to some other part of the browser that's responsible for registering a callback to be executed after 2 seconds in this case. But the point is that function returns immediately. We're not stuck anymore. This is not like the synchronous function. So for the purposes of the call stack, it's no longer there. And that's why we can move on. If we can move on, that means do async stuff is also complete. So we can remove that from the call stack, which means get coffee completes its execution. We can remove it from stack and move on to the next line, which is sing a song. And remember, we haven't gotten the coffee yet, but we get to move forward and get to singing a song. So the same thing happens as the previous example. Sing a song runs, it has a log. We see the log get printed to the console, and sing a song completes, and we get to remove it. And we didn't have to wait, right? We got to sing a song or see the log of sing a song without having to wait for the timeout. Now the set timeout, of course, at some point is going to resolve. So about 200 milliseconds later, just about, the set timeout web API comes back and says, hey, remember you gave me a callback and you asked me to call it after 2 seconds? Well, it's time. So it needs to be added to the call stack, right? Because that's where the stuff that gets executed goes. Yes, but the call stack isn't manipulatable by external things like web APIs. Instead, there's a different place, a list, a queue, something called a task queue. The task queue is accessible by all kinds of actors, including web APIs, including set timeout. So set timeout pushes the callback that we gave it to that queue. So that's the second piece of our async puzzle. The task queue. The task queue stores callbacks or jobs that come back from async operations, like timeouts and network requests and user events like click and hover, things that you can't really rely on the timing of, async stuff. And it's a queue, so it's not a stack, it's a queue. So it operates on a first in, first out basis, FIFO. So the callback function now is in queue, which is great, but how do we get it to the call stack, right? Because in order for something to get executed, it has to go into the call stack. I am so glad you asked, because the thing responsible for moving things from the task queue to the call stack is called the event loop. Whew. Yeah, I know. Are you still with me? I know that's a lot, but I'm trying to simplify as much as possible, and I hope that makes sense. Let's keep going. So here's how the event loop works. It checks the call stack when it's empty and looks inside the task queue for things that have been queued up for execution. If there's anything in there, it moves them from the task queue to the call stack for execution. In fact, the event loop is constantly running and checking in the background to see if the stack is empty. So the event loop picks up the set timeout callback from the task queue, pushes it onto the call stack. We execute the provided function, which logs, I don't know, coffee is here, async. That's what it is. Then it gets printed to the console and it gets removed from the call stack. And that is why the async example does not freeze the app. The singing can start asynchronously without having to wait for the coffee to be ready. So we have the task queue where async callbacks can get queued up when they're ready. And we have our friend, the event loop, to thank to make sure that they get added to the call stack when the call stack is empty and we're ready to execute more things. And we do that in the order they're received. Okay, let's look at a better example where everybody works together. Maybe this one's a little bit more clear. Say we have a button with an event listener. We don't know when it's gonna get called, right? So it's completely asynchronous. A couple of logs. We have a start script and an end script. And then we have two timeouts, one with 1,000 milliseconds and one with 500 milliseconds. And the order really doesn't matter. So let's animate the sequence. Also pay attention to the timeline below. I'm trying to visualize the timeline for you as well. So call stack is empty, task queue is empty, the event loop's got nothing to do, life is good, so far so good. This is the calm before the storm. The browser loads, it starts executing our scripts. No function is invoked yet, just registration of an event listener. Then we get to this console log, gets added to the stack. We print the thing to the console, gets removed from the stack. Then we get to our first timeout. That's called, gets added to the stack. It registers a callback with the set timeout API to be executed after 1 second. Then it gets removed from the call stack. We forget about the callback, right? Same thing with the half a second timeout. Gets added to the call stack, registers another callback with set timeout, then it gets removed from the call stack. Then we get to the end where the end script log is called. That also gets printed to the console, then remove it from the stack. So the event loop now is checking to see if there's anything to do, but there isn't, right? And pay attention to the timeline. It keeps looping, it keeps checking. Say nothing happens for 500 milliseconds. After the first 500 milliseconds, the set timeout callback for this line gets moved to the task queue. So the event loop checks the call stack and says, oh, there's nothing here. It's empty. Let me see if there's anything in the task queue. And of course there is. It picks up the callback that belongs to the second timeout from the task queue, pushes it onto the call stack, it gets executed, and then it gets removed from the call stack. Let's say, I don't know, 200 milliseconds or so later, the user decides to click on that button. So remember, one of the timeouts has expired, but the second one hasn't yet. The event listener for the click event is then added to the task queue. So we have one thing in there. The event loop is checking. It identifies it as a thing to be executed and does the same thing. Moves it to the call stack. The call stack executes it, logs the button clicked line, and then removes it from the call stack. And now another, 300 or so milliseconds later, we've left to reach the 1 second mark from the beginning of the script. So the set timeout callback for the 1000 milliseconds is now also moved to the task queue. The event loop again checks the call stack, can see that it's empty, picks up the callback for that second timeout, moves it from the task queue and pushes it to the call stack. It gets executed, we see the log, and then it's removed from the call stack. Is this making sense? I hope so. Thirsty again. We're almost done with our examples, but I have one or two more I want to show you. Next, I want to show you an example that comes up in interviews a lot, and it shows you exactly the difference between synchronous and asynchronous operations with like 4 lines of code. It's arguably simpler, but the results are weird. So here it is. If you run this code, even though you might think you get 1, 2, 3 in the logs in that order, you actually get 1, 3, 2. Let's investigate why. First log gets added to the stack, executes, logs 1, we move on, no problem. Set timeout is added to the stack. It executes and schedules a callback to be added to the task queue after 0 milliseconds, right? Basically right away. Even though it's not exactly right away, but let's say it is. Let's say the callback gets added to the task queue right away. So we end up with something like this, right? The event loop still has synchronous code to go through, even though it's not in the call stack yet. And that's a really important thing to remember. It needs to finish reading the script and executing all the synchronous function invocations before even checking the task queue. So obviously that includes the second console log. So that needs to get added to the call stack first. So the set timeout callback needs to wait even though it was ready before the third log. So log 3 gets printed and gets removed from the stack. Then, and only then, the event loop is allowed to move to the second log, execute it, and now we're done. And that is why we see 1, 3, 2 instead of 1, 2, 3. Hope you understand now that the set timeout with even 0 delay is still an asynchronous operation, and it needs to be executed after all the synchronous calls. So let's pause here and review all the concepts that we've talked about so far. Call stack. It keeps track of what's being executed and their order. Any nested function call from within the function being executed at that moment gets added to the top of the stack. Last in, first out. The task queue. It stores callbacks or jobs that come back from asynchronous operations like timeouts, network requests, or user events, or events in general. And by the way, I need to make a quick point about the task queue. There's something called a Microtask queue. That's reserved for promises. It's very similar to task queue, but instead of callbacks, it stores promise resolvers. And it gets priority over the task queue. Quick example here, we have a start script gets added to the stack and gets executed first. Set timeout callback gets added to the task queue after 0 milliseconds. The promise resolver gets added to the Microtask queue. And then the second resolver also get added to the Microtask queue. Then the script ends, so that gets added to the stack, executed. Now the event loop has a few things to choose from, right? Which one does it go for first? The answer is the Microtask queue. That gets priority even though the task queue got a task in it first. So the order actually doesn't matter. It's Microtask queue gets priority. So the first promise resolver moves to the stack and gets executed. Then the same thing for the promise 2. Then finally, the event loop can move on from the Microtask queue to the task queue and the timeout callback can be executed. Let's actually see this code run. I'm gonna copy paste this over to my browser. Start script, end script, promise 1, promise 2, set timeout, right? So even though, again, set timeout was here first, let me do this so I can hover, bam. So even though set timeout is written above the promises, right? The point is that promises will get executed first before the set timeout. So bam, hopefully that's clear. And lastly, the event loop is the guy that keeps checking the call stack for when it's empty and there are no more synchronous calls are coming, and moves to the tasks from Microtask queue and the task queue in that order and moves them into the call stack. It's basically the browser's assistant, right? It makes sure that the next most important thing gets executed and gets in front. And the order is first it executes all synchronous code, then it processes microtasks, then finally it processes the macro tasks or stuff that's in the task queue. Now you might think, okay, that's cool, Sina. That's cute. You got your little animations there. You get to spend some time on them. You work on them. You make them all pretty. I can't visualize my code, right? So what's the point here? How am I supposed to use all this visualization you're doing here? My code is way more complicated than that. How can I use this in my day-to-day? Well, Craig, what if I told you that there is a way to see how your code is getting executed without having to spend weeks and weeks and an unreasonable amount of hours like I do? Well, there is. Come with me to the browser, right? Let's see. I'm gonna go back to our fun 1, fun 2, fun 3, and I'm gonna write something here called debugger. Right? Writing debugger is basically like putting a breakpoint in your code. It pauses at this point. So I'm actually going to switch sources. I see the code for this page. It's this, breakpoints. In case you're not familiar with breakpoints, during execution, if you have a breakpoint, the engine basically pauses and gives you a chance to monitor your execution. So we go back to the console. Debugger is basically that. So I'm going to pause my code as soon as it reaches here. So let's execute this. Bam. So debugger says, I'm here. What do you want to do with me, tough guy? There is a little button here. There's a bunch of stuff here. There is one that says, if you hover over it, step into next function call. So from here, what do we expect? We here expect for fun1 to be called. So you can click on this and go to fun1. It pauses here. If I click on this, it goes inside fun1. So now it's executing it kind of like the animations I have, except now this is in Chrome DevTools. So what happens if I keep going? If I keep going, I'm invoking function 2. So let's go there. Function 2 gets executed, and within it, we have a nested call to fun3. So let's keep going. Fun3. So I'm going to pause here. I'm not going to keep going because I want you to see this. There is a thing called call stack. Would you look at that? The thing I've been talking to you about this whole evening. So fun3 fun2, fun1. This is our stack. This is exactly like I've been showing you. And what's fun about this is, so obviously this is the sequence of function calls that have been invoked. You can actually go back and you can see where something was called, and you can investigate the scope of that function and see what was happening at that point. So I'm going to press play here, which basically goes through and finishes the script. Let me go back to the console. I'm going to rewrite this, and I'm going to pass a parameter hello to function1, and I'm going to call this, I don't know, param, right? It's late and we're all tired. You've been listening to me for what, 20, 30 minutes now? So let's run this now. When we get to debugger, let me get rid of these. I'm gonna keep going. Let's go into function1. In function1, by the time the debugger gets here, I see the param. I see param, something called param, and I see the value of what I passed into it. Why is this useful? Because when you're debugging your code, you can actually pause everything and you can see the call stack and you can see who called what. If you have a function that's reusable, that's getting called from different places, you can investigate to see who called it. The chain of nested function calls is sometimes really important to follow if you're trying to debug something. So the ability to see the call stack and how you arrived at a certain point in your code is really important, and I'm here to tell you, you don't need me to make animations for you. You can actually do this yourself. Thank you, Chrome DevTools. Thank you very much. Everything I showed you today with set timeout, you can replace with any other async callback. The same principles and the same mechanism applies to any other callback function, whether it's from the fetch API or the DOM API or anything else you can think of that is asynchronous using callbacks, the same mechanism applies. The reason why I use set timeout in these examples, and I think other people do that too, is because it's really easy to demonstrate. And lastly, why is all of this necessary? Why do I need to pay attention to this? Why should you learn about the event loop to begin with? Like, who cares how the event loop works, right? And what it does and how it does it. It's actually a really good question. It's one of the most requested topics, just looking at my own comments on my own videos. Plenty of people have asked it. Plenty of people have tried to explain it on YouTube. So the question is why? Sure, it's an interview question. I know it comes up a lot, but just because some jackass decided to ask you a question about the event loop during an interview doesn't mean it makes it a good question, except for that moment because you were probably trying to get the job. But really, why should you care? And those are, again, really good questions. You should be skeptical of information just getting thrown at you. In this case, I would say, like most of the other videos in this series, that it's about understanding our tools and how they work. The event loop is basically the reason why we can do asynchronous JavaScript. And if you know anything about modern JavaScript, you know that so much of it is asynchronous. It's everywhere. So to know how the JavaScript engine works at a fundamental and practical level, it helps you produce better code when you write it and understand the code easier when you read it. And here's a link to my full explanation of asynchronous JavaScript in case you want to see more of my face. I hope you learned something today, and I hope that this helps you think through the code that you are reading or writing a little bit easier and maybe a little differently. Hopefully this helps you understand what's going on when you run into a bug that is caused by a race condition or some timing that you weren't aware of. Send me your questions down below. This was a longer episode than I had anticipated. It wasn't an easy one to shoot, especially with the two guys talking to each other. That was episode 18. Of 20 things JavaScript developers should know, but probably don't. The next episode will be on functional programming. We're going back to functional, specifically imperative versus declarative, especially important for those who are coming to JavaScript from an object-oriented background. Hope to see you then. Until next time. Salut.